Welcome to Chemistry 112. We're going to have a pretty simple class today. We're not going to take the whole class period. I was looking at the syllabus. We're scheduled actually to finish chapter 14 next week, so we're running a little bit ahead. But that'll give us some time to really go through some of this stuff, and that we'll go through, we'll finish this chapter, and then we'll have some time to look at some of the achieved homework. Because some of this is a little tricky. We won't even get to this lab till lab 3, but lab 3 will be chiefly a rate law-based lab. We'll look at acetone, acid, and iodine, how iodine is decolorized by a reaction between acid and acetone. And we're going to vary the concentrations of each of the 3 components and see how that affects the reaction rate. And we'll determine the reaction orders for each of those. But that won't be for a couple weeks. So, because we still have to finish our lab 2, which is our molar freezing point depression lab. So that one's, you got to be very careful and make sure you don't spill anything and all that, or else there's plenty of sources of air where that could throw things off. So, but okay, let's start off with talking about rate laws, rate mechanism. So the whole point of this chapter is really to understand what is going on. We have an overall reaction mechanism. Whenever we write, methane plus oxygen burns to get CO2 and water. That seems pretty simplistic. But what actually goes on in there is infinitely more complex, because you got to think about that. When you're burning something like methane, you have to break 4 CH bonds. You have to break at least, let's see, you have to break, I'm trying to balance the oxygens. You have to break at least 2 sets of OO double bonds, and you have to make 2 CO double bonds and 4 HO single bonds. Imagine that if you just imagine dicing this up like you're a chef and then throwing it in a pot and mixing it, yeah, that could work. But things don't actually happen like that. They typically go 1-2 bond cleavages at a time. So we're looking at a hot mess of stuff that has to happen. The question is, what happens first? And the answer to that only comes by clever analysis of kinetics. Now, we won't go, that reaction is actually way more complex than we're scheduled to deal with here. If we ever go into physical chemistry, yeah, maybe we'll actually have time to look at that. But right now, that is actually a very complex reaction that goes on, that involves radicals and all sorts of craziness. Because we know the methane we burn on Bunsen burner goes pretty fast. Once you light it, it just goes on its own. We don't ever have to worry about it slowing down. As long as there's enough methane and enough oxygen, it goes. So the thing we look at is we're going to look at, say, the rate law. The rate law that we tried to determine about the second thing we did in this chapter. The rate law relates to the actual physical atomic level mechanism. The overall chemical reaction is just a generalized picture of that mechanism. That's the overall reaction mechanism is like the state function. It takes the starting point and the ending point, and that's what we look at. The actual reaction mechanism looks at all the tiny steps in between. The overall reaction tells us, here, I started in Mackenzie, I drove to Gatlinburg, starting ending point. The reaction mechanism says, well, then I turn, I go onto the highway, I go to Nashville, go through Nashville, I keep going, and I take these turns, and I take this exit. It's all the complicated, intricate steps to get there. And so our rate law will tell us something about how do we actually get there. If we just look at a simple reaction, this one's relatively simple compared to the burning methane. How ozone is destroyed in the atmosphere by sources other than light. We all know ozone, hopefully we know ozone, that absorbs ultraviolet light, cleaves itself apart into oxygen, But there's another source of cleavage in that a monoatomic oxygen. So this is a single oxygen atom, not very stable, highly reactive, but a single oxygen atom will react with ozone to form 2 moles of oxygen. This is a way to degrade ozone other than light. Now, if you look at this by itself in the atmosphere, this reaction rate is normally very slow. That has to do with stabilities. It also has to do with the concentration of monoatomic oxygen. It's not very common, not very stable. You have to have one monoatomic oxygen bumping into an ozone. There's a bunch of other molecules up there. This is normally very slow. However, if we get pollutants, now this may be before a couple of your times, but back in the 90s, we had to worry about hairspray destroying the ozone layer. That hairspray had certain pollutants like CFCs that would essentially get into the atmosphere. They're long-lived, and they would degrade the ozone layer. And we had some holes in the ozone layer above the Arctic Circle. Now, also, there's nitrous oxide gases that can do a similar thing. When we put these guys, these are catalysts, and suddenly the reaction rate becomes very fast. However, a catalyst doesn't typically show up in the overall reaction. A catalyst doesn't show up in the overall reaction because a catalyst, as we'll talk about later today, is consumed in the first step, but reformed by this last step. So it has a net effect of 0 in the addition. We use it up, but then we get it right back. So it can keep being used, which is part of why the CFCs and nitrous oxides were such a problem. It wasn't just consumed and done. It gets consumed and then reformed and consumed again and reformed. And even when they froze into crystals, then when night came, when the sun rose back up, melted them, and they started reacting again. So we have to find a way to remove them. So based on the overall reaction mechanism, if you look at just this reaction by itself, you would say, oh, it should be first order in O and first order with ozone, that it needs those 2 molecules to bump into each other to react if we're looking at this. However, that is not the actual rate law when pollutants are present. By itself, without a pollutant, without a catalyst, that is the rate law. Those 2 guys have to bump uglies to react. But with a catalyst, that's not the case, as we'll see. The first thing we'll get to is what's called a elementary reaction. So the overall reaction mechanism is split into what we call 2 elementary reactions. You know, elementary, my dear Watson, it's so simple that what we see is what it is. It's the simple truth of what we see. An elementary reaction is a reaction that shows the literal collisions on the atomic level. You show an elementary reaction, it cannot be broken down into any simpler reaction. It's this atom hits this atom and thus reacts. So looking at the overall mechanism of this, when we have a pollutant, we can split this into 2 steps instead of 1. When we look at all the elementary reactions, we can see the reaction mechanism. So what we see in the case of chlorofluorocarbons, we have a chlorine radical. When a chlorine radical bumps into an ozone, you form a chlorine monoxide radical and oxygen. Now that chlorine monoxide radical can bump into an oxygen, a monoatomic oxygen, to reform the chlorine radical and does oxygen. If we add up those two steps, we see chlorine on the left, chlorine on the right. They are removed. Chlorine monoxide on the right, chlorine monoxide on the left. They are removed. You add them up, you get the overall reaction mechanism of O plus O3 goes to 2O2. So you get the same overall reaction, but it occurs through two different steps that are much faster. The same thing with nitrogen monoxide. Nitrogen monoxide bumps into an ozone, forms NO2 and oxygen. Then O2 bumps into a monoatomic oxygen, reforms the NO and forms O2. You remove this guy from the left and the right, you move that guy from the right and the left, you get the same overall reaction, a different mechanism to get there. And so the big thing is that these reactions go through a series of steps where we form what's called an intermediate. An intermediate is a product that doesn't show up in the reaction, overall reaction, because it is consumed before the reaction is over. It hangs around. It's the middleman. It hangs around just long enough to move the reaction on. So you can capture the intermediate on occasion, but it's usually in really low concentration because as it gets formed, it's typically consumed. And all of these reactions will have what's called the rate determining step, which is the slowest step of the reaction. And that's going to determine the rate law for the reaction. The rate determining step determines how fast the rate goes. If you go in the book, you look at this, they typically explain this, and like you go into an airport. Like if you're going in trying to get on a plane, if the TSA is taking super long and so long that you're right before the boarding of the flight, the TSA is going to be the thing that determines how fast you can board that plane. As soon as you get out, even if you're waiting 5 minutes, 10 minutes there, you've already been in the TSA for an hour, and that's going to keep you, that's going to determine how fast you can board that plane. However, if they say there's no line, no one's flying for whatever reason, you go through the checkpoint really quickly, then you're sitting around waiting to get on that plane until they start boarding. So depending on which step is the slow step is going to determine how fast you can board that plane. And so right here, looking at this rate law, looking at the energy diagram, this first step has the highest energy barrier, has the highest activation energy. So it takes a while to get to here. That's going to determine how fast it goes. But once it's in this little valley where the intermediates form, there's a very low activation energy to push it down. So it could technically still hop backwards, but it could also hop forwards and produce more energy going that way. Now, this is maybe not the best one. Maybe this energy should be a little bit lower. Maybe this energy should be a little bit lower still than that, but it's just an idea to show you that if we did one step, the energy would be much, much higher than where we have here. Instead of this twin peaks, we have just one big peak that towers above both of them. So the one-step mechanism is very high activation energy. The two-step, significantly lower. And so it happens significantly faster. Now, here's the beauty of this. In each elementary reaction, the rate law of an elementary reaction is directly dependent on the stoichiometric coefficients. So breaking down that into two reactions. Rate of the first reaction is equal to the constant of the first one times the catalyst, nitrogen monoxide, times ozone. The rate of the second reaction is equal to the second step is equal to the K of the second step times the intermediate nitrogen dioxide and monoatomic oxygen. In these elementary equations, the coefficients are directly determining the order. However, in the overall reaction, they're independent because the overall reaction combines all the steps. The overall reaction combines all the steps. In the elementary reaction, it cannot be broken down. So we're literally saying this atom hits this atom and reacts. So that we're saying for that first reaction, NO hits ozone and reacts. The K kind of is the orientation factor and the activation energy all in one to say how many of those collisions are effective. Now, for this reason, because the elementary reaction is based on the order, term molecular reactions are rare. Because imagine if you have to bump into 3 or more atoms to react at one time, what's the likelihood of 4 atoms hitting at just the right orientation? Just the right orientation to react. What's the likelihood of like 4 atoms colliding just at the right time? I mean, how many Beatles do we have? I mean, arguably we have at least one band, the Beatles. How many bands of that degree of famousness do we have out there where 4 people come together at just the right time to make some world-changing music? So how many times are we going to have 4 atoms hit together at just the right time, just the right energy to make this reaction occur? It's not super likely. So oftentimes we're going to look at mostly bimolecular or monomolecular reactions. Each elementary step will have a different rate constant. And in every reaction, one step will be called the rate determining step. Typically, this is dependent on the size of the rate constants. Which rate constant is significantly faster? So in the case of here, looking at actual data, I think, if I remember right, K1 is 3.5 times 10 to the negative 15th. K2 is 9.3 times 10 to the negative 12th. So just looking at that, that is something like 3,000 times faster, almost 3,000 times faster. Step 2, meaning that by the time one molecule of step 1 has reacted, it's going to react to step 2. Sure, this is a small number. This is a small number. But comparatively to this guy, it's 3,000 times faster. So step 1 happens. We form a product. I mean, we form the NO2 intermediate. While step 1 is going to go again, happen again, and form a second guy, before the step 1 can form the second guy, step 2 has already occurred. So before a second person can be scanned by the TSA, the first person has already boarded the plane. Sure, he had to wait 5 minutes, but he didn't have to take off his shoes to get on the plane. He didn't have to go through the body scanner to get on the plane. He didn't have to take out all the change from his pockets to get on the plane. So the first person has already boarded the plane by the time the second person has made it through the TSA. That's what it's saying. If the second step is fast and the first step is slow, relatively speaking, then the first step is controlling how fast people can board planes. In this case, how fast this reaction can occur is based on just on that first step. As I said, the rate determining step is the bottleneck, how fast this can occur. I did that. Yeah. In this case, the rate determining step, meaning what that means. When we look at the reaction rate, the rate law for this reaction, the rate law is independent of the amount of monoatomic oxygen. It's independent of the NO2. So the rate law is equal to K1 NO times ozone. And because NO is a catalyst, meaning it is consumed and regenerated by the end, NO's concentration essentially remains constant. And because of that, K1 can become what we call K1 prime, where it's essentially K1 times NO, however much catalyst we have in there. Meaning, if we look at the rate law of ozone degradation, it's essentially rate equals a constant times the amount of ozone is present. So the ozone degradation is only really dependent on the amount of ozone present, not on anything else. Not on anything else, because NO is, once you put it in there, it's going to keep reacting. And K1 is only dependent on temperature. So in this case, if you did a rate law, you would find this is first order in ozone, zero order in monoatomic oxygen. So if we change the amount of monoatomic oxygen in there, you would see zero change to the rate. But if we change the amount of ozone in there, we double the amount of ozone, we double the rate. We triple the ozone, we'd triple the rate. And so that's when we look at the actual reactions, we could use that to kind of determine the rate law and understand what's going on. Though, a quick note for what we're going to be using this for. Any reaction mechanism must match both the overall reaction and agree with the rate law. So you can't have a reaction mechanism that's super crazy that doesn't end up at the right products, that doesn't like consume way too much ozone and not produce it back. But let's see if I have an example. But it also has to agree with the rate law. I'm going to actually show you, I'm not sure if I have this on here, so I'm going to actually show you one that is commonly used, that it's try to make sense of what's going on. Okay, so there's a reaction that occurs that says NO plus, I think NO2 plus CO goes to, if I remember this right, goes to NO and CO2. If I remember this right. You don't have to write this down, and if you measured the rate law, you would find that the rate is equal to K NO2 squared CO 0. So not only is it not dependent on carbon monoxide at all, but it's doubly dependent on NO2. I'm trying to remember if that's right. I think that's right. Okay. So what they determined the reaction mechanism to be is that step one NO2 bumps into another NO2, and it forms both the intermediate NO3 and NO. So that would be our K1. And this is going to be our rate determining step. The second step, which is the relatively faster step, is our NO3 can then bump into our carbon monoxide to reform our NO2 and our CO2. So this guy is our intermediate that doesn't hang around very long. And because of this, we see two NO2s being consumed, but an NO2 being reformed in the end. So when we sum up all the things, we can cross out one of these, cross out the intermediate, so we have the overall reaction being NO2 plus CO goes to NO and CO2. So it still matches the overall reaction mechanism, the overall reaction, but the rate law, it matches the rate law as well. So what we actually see is NO2 bumping up, forming an intermediate in that, and that explains the NO2 squared. That explains the NO2 squared because two NO2s have to bump into each other. Because this step is slow, this step is fast, the amount of CO doesn't really matter because as soon as this NO3 forms, bumps into a CO, reacts. That's a perfect example of this in action. Another one, a common one that we see is N2 plus 3H2 goes to 2 ammonias. And we see the rate law. The rate law is actually just K, like N2 to the it might even be half power. Might be something like crazy half power because one N2 breaks into two N's. But because the rate law is actually step 1, N2 must break into 2 N molecules. And then an N molecule plus a hydrogen, it's like a half mole hydrogen adds an NH, and then we do it again. NH plus a half H2 forms another NH, and then NH2 plus another half hydrogen forms NH3, and then it leaves. That basically the slow step is the breaking apart of the nitrogen, So even though we have 3 times as much hydrogen in the reaction, if we're controlling the reaction by how much nitrogen breaks apart and how fast nitrogen breaks apart, then that is the only thing that really matters when it comes to the speed. The amount of nitrogen present is the only thing that matters when it comes to the speed. Sure, the hydrogen has to be there. If we have no hydrogen, reaction will not go. But the only way to make this go faster is to add more nitrogen. The only way to make this go faster is to add more nitrogen because the first step in that case is the rate determining step. Those are just real world examples of this stuff in action. Now, the easiest thing to do is a slow first step. If the first step is slow, it's very easy to understand. So just hypothetically, A plus B goes to C, C plus D goes to E. So the overall reaction is A plus B plus D equals E. But we see the rate law is just in terms of A and B. So maybe the first reaction is slow, happens once every minute. The second reaction is fast, is once every 10 seconds. Saying every time C forms, it is used up rapidly. It has no time to get built up. That means D will not really, the only way D can affect the rate is if D is essentially 0. If D becomes so dilute that compared to A and B, it's like almost none. There's almost no D's. So that's the only time D will actually have effect. But in this case, when the first step is the slow step, the rate law is just dependent on A and B. The rate law is just dependent on the first step. The second step becomes a little bit harder. If the second step is slow, both steps will matter. Both steps will matter because usually if the first step is fast, it also has a rapid equilibrium, meaning it can go forward and backwards. So here's the tricky part. So the forward reaction is defined as A plus B. The backwards reaction, which is rate of -1, is equal to the K to the inverse reaction, C. However, the rate of the second reaction is C times D. And the problem here is we don't know the concentration of C. We have a chance for the intermediate C to build up, but we do not know how much C we have at any given time. This is a problem brought about by the fact that we didn't put C in there. We don't know how much C is present because we didn't start with C. And we have a competing reverse reaction. However, what we can do is we're going to make an assumption that if this is a rapid equilibrium and this is at equilibrium, which this is something we'll get to next chapter, chapter 15. What does equilibrium mean? Equilibrium means when the rate of reaction for the forward and the rate of the reaction of the reverse are equal. If the forward rate and the reverse rate are equal, you stay in place. It's like a treadmill. You walk at the same pace at the treadmill's moving, you don't move. If you're running too fast, you're going to run off the treadmill. Going too slow, you're going to fall off the treadmill from the back. But at equilibrium, you're moving forward at the same pace it's moving backwards, and you stay in place. Now, for that reason, if we are at equilibrium, we can set the two rates forward equal to the reverse. And if they're equal, I can set the concentration of C equal to the concentrations of A and B times the relative constants. Now, if I solve for our C, we get an ugly ass constant here of K1 over K minus 1, but it gets it in terms of A and B. And so when we plug this in to the rate 2, we get A plus B, A times B times D. So let me go to the doc cam and kind of show you the systematic steps of what I'm actually doing there. Because I'm just, you don't have to know this, but it's kind of so you see what all that mess on the screen is doing. So we're saying this is equal to this. And because we do not know, and we want to solve for this one. We want to solve for this guy. We know how much D we put in there. We know exactly how much D it has. But we don't know how much C it has. So we need to solve C in terms of something we know. So to get C, we have to divide both sides by K minus 1. K minus 1 is just a constant. Just a constant. So that gives us that K1 over K minus 1 times A times B is all equal to the concentration of C. So if I know this constant and that constant, which we can, and I know how much A and B I put into the reaction, we know exactly how much C is there. We know exactly how much C is there. From there, We're plugging that into there. And that's where we get the thing you see on the screen, which is K1, K2 over K minus 1, A, B times D. And because we don't actually care about each of these K's individually, we can just call that K. We can just call that K and simplify that down. And that's what we end up doing. But long story short, if second step slow, all reactants present. If first step slow, only reactants from the first step are present. So, if it was a three-step reaction and the second step is slow, then only reactants from the first and second step are present, and so on and so forth. You only consider the reactants from the initial steps up until the rate determining step. This is a really hard concept to kind of get, which is why we'll look at some of the homework at this after we finish that. So last few things, we have some examples. So match the rates with the correct equation. So 3 examples. All of them have the overall equation of A plus B goes to D. 2 A's and 1 B goes to D. Now we're trying to match which rate law matches which reaction mechanism. So remember, the rate determining step is the one that determines what we have. So in the first example, A plus A goes to C. That is the rate determining step. Then C plus B goes to D. In that case, the first step is slow. So which reactants should be present in the rate law? Just A. In fact, there should be 2 A's. Now, which example has 2 A's in the rate law? Well, that'd be B. Rate law B has only 2 A's. Example 2, we have A plus B goes to C, and then A plus C goes to D. But the first step is the rate determining step, the slow step. So if the first step is slow, it's only going to include A and B. So that A and B, for example 2, is rate law C. And that leaves the last one being A. But let's look at it. A plus A goes to C. B plus C goes to D. Now, that right there, since the second step is slow, all of them must be included. So we have 2A and the 1B. We don't include the intermediate. There is one other option here that I did not include, but it would result in the same answer. I could have wrote this. A plus B goes to C, and then C plus A goes to D, and that is the rate determining step. Once again, it would include 2 A's and 1 B. Slightly different way to occur, but it would have the same rate law. So right now that is actually indistinguishable. The only way you could figure that out is by looking at C, by trying to capture some C and see if you could form it. One way to do that would be to put only A in solution and see, do you end up with any of their intermediate? If you need B to form the intermediate, then it's this reaction. If you don't need B to form the intermediate, then it's the other reaction. But that is getting into some complex stuff well beyond where we're going to have to worry about. Now, I think the last, well, okay, one more practice problem. So we have, this is something you will need to be able to do to some extent. I want to try to probe your mind. I want you to start to try to think through some of these guys. Propose a two-step mechanism for the following reaction. 2 NO2s plus F2 goes to 2 NO2Fs. With a rate law that has NO2 first order NO2, first order F2. So here's the thing. You do not have to be right. You don't have to make the most sense. You don't have to have molecules that you think are the most stable in existence. You just have to propose something that would fit that. So just looking at that. Based on the fact, going to the .chem, based on the fact that it is first order in NO2 and first order in F2, we're going to have a slow first step because it doesn't include all of them. We're going to have a slow first step. And whatever happens in the first step, these two must react. So whatever is going to happen between the second step is going to be the hard step. So the first step, we kind of got it going. Second step, you're going to have NO2 plus some intermediate. So maybe you have something crazy like, I could imagine this, I don't think is particularly stable. You could have this NO2F2, and then you'd have NO2F2 bumps into that to form our 2 NO2Fs. That's one possibility. I could imagine another possibility equally as likely. NO2 plus F2. This one might be more likely, in fact. You form one NO2F and one F radical. And then you get NO2 plus F radical goes to their second NO2F. So there's a product. Here's my intermediate. In this case, we just formed an intermediate, and then we have two products. Neither of these is necessarily more right than the other until you actually try to test for them. There are ways to capture radicals. There are ways to try to capture these intermediates. And so you could put a radical capture somewhere in there and try to see, do I get an F radical? Or do I get some unstable NO2F2 structure? The important thing is the first step, which is slow, has NO2 and F2. The second step has some intermediate reacting with the other molecule of NO2 to form our product. I said, I'm not expecting you to know everything about the most stable compounds out there. I'm just asking you to think about it. And this is probably the last slide, is catalysts. Essentially, we've been talking a lot about these catalysts, but what do they actually do? How do they speed up reactions without being consumed? And the big idea for catalysts or catalysis is they provide a lower activation energy with an alternate mechanism. They give you a different mechanism to get from step 1 to step 2. So they step 1 to step 1.5. The example I give here is the red one is the traditional O to O zone. We have a big high activation energy barrier. But when we put in the catalyst, it has a much lower barrier to give to products. Same starting point, same ending point, same product, same reactants, same energy. It just makes it happen faster. So a catalyst, you only need very little. A catalyst doesn't give you more energy. A catalyst will not give you more products than you should have. All a catalyst does is make it happen faster. You get to the end at a faster rate. For you biology people, enzymes, all those are catalysts. What do? They grab one molecule and put it in an active site that can easily be attacked by something like, oh, this is going to attack and cleave this bond. Oh, this is going to push a phosphate on. Just holding it in a way that we don't have to worry about that orientation factor and lowers the amount of energy it needs to collide. There's many of heterogeneous catalysts, like metal catalysts, like fluidized bed reactors, where you run the liquid over that, or you run the gas over that. What is the catalytic converter in the car? But essentially a metal catalyst that when you push your exhaust out of your car, it reacts there, and we try to change the chemical properties so it's less toxic, less pollutants as it goes through. There's many biological catalysts, but even elephant toothpaste, if you Google that, elephant toothpaste, we've done this chemical reaction oftentimes around campus, but it's hydrogen peroxide plus some soap, and then we put in the catalyst, potassium iodide. Hydrogen peroxide typically oxidizes itself and goes to water and oxygen gas. This will happen over a long period of time. You put a catalyst, it happens all at once. You catch that oxygen in bubbles, and the bubbles expand and explode outwards. That's your elephant toothpaste. It's all based on a simple catalyst. Okay, one more mechanism. So, propose a mechanism for the decomposition of hydrogen peroxide. Doesn't have to be accurate, doesn't have to be perfect. It just has to fit what we got. So the reaction is 2 peroxides goes to 2 waters and oxygen. And the rate law has to match K, 1 peroxide, and iodine. Going to the dot cam. So looking at that, we already know where our starting point is. We already know that. We're going to have some amount of intermediate, probably some sort of product there. And we're going to have H2O2 plus our standard intermediate is going to go to the other products. Now, I happen to remember this, I think I remember this. And I think what we form, but in the first step, is 1 molecule of water and the intermediate. But so what could happen? You could either slap those 2 together, but then you have a whole lot of craziness going on. So what might actually be simpler is, what products could we form? How do we form this? The products. We have to lose 1 oxygen from H2O2, and we have to combine 2 oxygens from here together. So you could have one of 2 possibilities. You could have something like this, H2I, or you could have OI, depending on whether you form oxygen or H2O. I think we actually go through this one, and H2O, where we form OI and H2O. From there, OI minus can react with this to form another H2O and our O2 and reform our I. But however, whatever the crazy intermediate you form, you have to match the rate law and the overall reaction. The overall reaction. So that's what we have here. Okay, so that's the PowerPoint. So there's that. So let's go to Achieve. Achieve, pulling this up. We'll go through a couple problems on this. Throw this over to, oh, come on. Okay. Okay. Oh, crap. I didn't want to do that. Okay. Okay. Then looking at this. So there's a lot of things we could look at. I want to look at the harder stuff. We could look at a rate. We already looked at a rate law problem last class. Instead of looking at, we could look at some integrated rate law problems, but I'd rather look at reaction mechanism problem and maybe a, if we have time, we'll go back for one of these, the rate law dependence. So let's look at 13 and maybe we'll do 13 and 14. There's a couple of them. So let's start with 13. So number 13 on here that says, consider the following mechanism. A plus B goes to AB. AB plus C goes to AC and plus B. Then A plus, so the overall reaction is A plus C goes to AC. So what species is the intermediate? So in order to think about this, an intermediate is something that is formed in the first step and consumed in the second step. It doesn't exist in the overall reaction, but it isn't present when we start. It is something that is formed when in the first step. So looking at that, the only thing that formed in the first step is our AB. Now, a catalyst also isn't present in the overall reaction, but it is present in the first step. It is consumed and then reformed by the end. Consumed and then reformed. So B would be our catalyst. So hard and fast rule, intermediate first shows up on the right and then shows up again on the left. A catalyst first shows up on the left and then ends up on the right. So the intermediate starts on the product side, ends on the reactant side, and the catalyst starts on the reactant side and ends on a product side. So B starts on the reactants here, and on the second step, it shows up again on the product. In biological terms, you'd be writing something like enzyme plus substrate forms an enzyme substrate complex, and then it goes to enzyme, the enzyme substrate complex breaks apart into the products and your enzyme again in biological terms. Okay, let's look at 14 and maybe 15. Consider the following elementary reaction equation. Okay. H2O2 breaks down to H2O and monatomic oxygen. What is the order with respect to H2O2? Well, because it is just one and it's elementary, we can just say it's one. We don't have to think about that. What is the overall order of this reaction? Well, the overall order is the sum of all the reaction orders. There's nothing else in it, so it's just one. And then it's asking to classify this as bimolecular, unimolecular, termolecular. Well, there's only one order, so it's unimolecular. So that one's way too easy. But that's good. That's always good to have a really easy one in there. Give you confidence. Okay, so here we go. Determine the rate law for the overall reaction, where the overall reaction is rate constant is K. So in this case, just like we just did in class, we have A plus B goes to C, A plus C goes to D. The first step is slow, the second step is fast. So what we'd have to do is write down the rate law. You could break it down into step one is K, A times B, and step two is K, A times C. But we only care about the slow law. So we're going to just worry about the first step. So K, A, put in brackets, B, put in brackets. We don't need to raise them to an order. It's understood that they're one. However, if it was, you would then superscript a squared. Please make sure to put them in brackets. That's probably the least likely to screw this up. Here's a quick hint. Whenever we're using brackets, brackets tells us that means the concentration. Brackets is the concentration of A times the concentration of B. And let's make one more. Okay. Slow step. Slow step is the second step. So we can simply say K. I'm going to check this. And then we'll put A, B. Now because there's an A in the second step and an A in the first step. Did I lose my bracket there? Okay. What's going on here? Okay. If I can raise that squared. Okay, yeah, raise that squared. Bracket there. Nope, wrong bracket. There we go. Let's see if that works. So because I have to include A and then B. We don't include the intermediate, A and B. That's a hard, that usually works on most cases. Usually works on most cases. Let's see what else. Okay. I'll leave this one for you guys and I'll run through one more problem. Go back into the question 12. Question 12 is a certain reaction has an activation energy of 54.51 kilojoules per mole. So EA is 54.51 kilojoules. At what Kelvin temperature will the reaction proceed 7.5 times faster? So We want it so K2 is equal to 7.5 times K1. So T2 is what we're solving for. And T1 is 331 Kelvin. Our reaction is what? Like ln, I can do K, if I do K2 over K1 equals EA R 1 over T1 minus 1 over T2. Please note, if you flip-flop the order of one of these guys, if you flip-flop the order of one of these guys, you're just going to flip the sign. If I say if I meant to say T1 minus T2, or if I meant to say T2 minus T1, it's just going to make EA negative instead of positive. You should always have a positive activation energy. But in this case, this is one of those ones, reason it out. If you have to do an inverse log and it's negative instead of positive, if the speed is faster, the temperature should be higher. If you get a temperature that is lower, you flip the order and you screwed it up. So reason this out. Reason this out. You should be able to tell whether the answer looks right. That if it's at a faster speed, it should be at a higher temperature. So let's look at this. We have everything we need. We don't have K1, but we don't necessarily need K1 because we're doing ln 7.5 K1 over K1, which cancels out. So we're doing natural log of 7.5. That's equal to, here's a big thing, make sure to turn this into joules. I just screwed that up. Okay, turn that into joules because I'm dividing by 8.314 in joules. 331 minus 1 over T2. Just down a bit. Oh, sorry. Okay, there we go. So let's start by doing the natural log of 7.5, which gives me, and don't round unnecessarily. Keep at least like 4 sig figs, just because rounding is a pain. Rounding too much changes your answer by a bit. So then I'm going to multiply by R, divide by my activation energy, and that gives us 0.003073. You'll see why in a minute. 1 over 331 minus 1 over T2. So I'm going to get 1 over T2 over here. So that means I'm going to have 1 over 331 minus that number. 0.000373. If you round unnecessarily, it's going to make a big difference. 331 minus 1 minus 0.000373. You get, this is a good sign. I have a positive number. 0.00271, we'll say 4. 1 over T2. So how do I get T2? I have to take the inverse. The inverse button is this little button here. Oh, you can't really see it on my right little button here. It's x to the negative first. That just flips it over. It's 1 over x. So my temperature is 368.5. 368.5. Had I rounded, let's say I rounded to 0.0003. 31 minus 0.0003. If I inverse it, if I inverse that, I get Okay, that one, thankfully, is not a big deal. That one gives me 367.5. But let's say I rounded this number to 0.003. If I take this number as 0.003 and inverse that, I would get 333. That's a big difference. If I just used 27 instead of 2714, I would have gotten 370.4. So the further digits out, the closer I get to the actual number. And remember that just because sometimes it'll let you get away with it, sometimes it'll let you get away with it and say, oh, yeah, that it's close enough, but sometimes they won't. I'm going to use 368.5, and that should be the correct answer. Done. So that is where we will go ahead and stop. We have technically 5 minutes left, but I got a place to be. So we finished this chapter. If you have any questions about the homework, feel free to ask. Otherwise, we will start chapter 15 early next week. We are ahead of the game, so but don't slack off too much. Thank you for your time. Bye.